Welcome to lecture 2.5, where we're going to introduce the concept of formal charge and introduce how we're going to approach it when we talk about carbon. Of course, the most common atom in organic chemistry. So to get started, let's talk about formal charge and compare it again to the octet rule, because there's a very important comparison between the octet rule and formal charge. So in the octet rule, as we discussed in the previous lesson, a bond is worth 2 electrons and a lone pair is worth 2 electrons. Now this also includes double bonds and triple bonds, but for now we'll leave it to this. And the idea here is that the octet rule and the formal charge rules are going to talk about different things. We're going to change our view on what a bond and what a lone pair is according to what we're trying to do in the moment. So the octet rule is talking about stability. It's talking about having an octet or 8 electrons around you. And it doesn't really care who those electrons belong to. Whereas formal charge, we're going to think a lot more about owning the electrons as opposed to just being surrounded by them. So with formal charge, a lone pair is akin to 2 electrons that are, as I'll say, in your pocket. It's if an electron is $5, then 2 electrons as a lone pair is a $10 bill in your pocket. It's your $10 to spend as you wish. Whereas a bond, it still represents 2 electrons, but it's 2 electrons that are being shared. Now, of course, as we discussed when we talked about bonding, this can be shared equally or unequally, but when we talk about formal charge, we're always going to assume that they're shared equally. And 2 electrons being shared means that actually this is only 1 electron that you own, let's say. So, if I want to have a comparison here, this is a $10 bill in my pocket, and the 2 electrons in a bond is like me holding a $10 bill, but my friend is holding the other $10 bill. And it's our $10 bill, and we can go and spend it, but we can only really spend $5 per person. So the important rule here is that while formal charge and the octet rule agree about what a lone pair is worth, they disagree when we talk about bonds. A bond is going to be 1 electron. And that's going to be a very key consideration. So when we think about an atom gaining or losing electrons, let's think about what that has to do with charge. Because at the end of the day, formal charge is simply the charge of the atom. So if you see a positive charge, we say it as a positive charge of 1 or a formal charge of +1. But being able to understand or predict what that formal charge is based on what's around the atom is the skill that we want to gain today. So the atom gaining electrons. If you gain electrons, it should be fairly straightforward that you're going to become negative, or you're going to gain a negative charge. But what does that look like, right? One common misconception that students will have is, well, let's say we're looking at this carbon, methane. Carbon connected to 4 hydrogens, an sp3 hybrid. Well, if I want to give it electrons, I could say, well, let's give it 2 electrons in the form of a lone pair. Right? I add a lone pair to it. Take a second to think about why this might not be so correct. Well, technically, it would, in theory, have a negative charge. It doesn't really exist, right? This violates the octet rule. I can't just add electrons onto a carbon that already has the octet rule. We could call this something like a pentavalent. So the valence shell has 5 things instead of 4, or an overfilled valence shell. In either case, this is not going to work. So this isn't going to make any sense. We can't make that work. Right? Well, what if I try a bond instead? Well, if I add another bond, I'm only adding 1 electron in that case, according to that carbon. But now, once again, we still overfilled the electron. We can't break the octet rule in this case. So what can I do? Right? It turns out that when we're talking about formal charge going forward, and this is going to be true for carbon, for oxygen, for nitrogen, and for the halogens, the only way that you can gain electrons, you gain electrons by trading a bond for a lone pair. And what do I mean by this? Well, let's take that same methane that we had before. And now what I'll say is, okay, let's count the amount of electrons that this carbon has. Right? And for now, we won't worry too much about the formal charge and the valence. We'll get there in a second. But we'll say that this carbon is surrounded by 4 bonds. So it has 8 electrons in its octet, which means that we're happy. But all of those electrons are in the form of bonds. That carbon doesn't have all of those electrons to itself, right? That situation would be a carbon with 4 lone pairs. And that wouldn't exactly be a happy carbon. But note that even that carbon wouldn't violate the octet rule. In this case, since it's all bonds, a bond is 1 electron, we actually have 4 electrons in the valence, is what I'll say. 4 electrons that belong to the carbon. So how can I make it gain electrons? Since I can't add things, we have to trade the bond for the lone pair. And to do that, I'll take that same hydrogen, or the same carbon, add my 3 hydrogens, but instead of the 4th hydrogen, let's give it a lone pair instead. Now what this does is it still maintains the octet rule. A bond and a lone pair, as a reminder, are the same thing in the, from the perspective of the octet rule. So trading them doesn't matter. However, from the formal charge rule, this carbon, which had 4 valence electrons, it now has 3 electrons from the bonds because it's being shared, and it has 2 electrons that both belong to the carbon since they're in the form of a lone pair. In total, that gives us actually 5 valence electrons. Awesome. So with that in mind, we can also think about the reverse process. How do you lose electrons? And in this case, it's the same thing. We're going to be trading a lone pair for a bond. Now, I'll talk about how you can use this understanding, the idea of trading lone pairs and bonds, to make formal charge easier, but that's going to come in the future lectures when we talk about the different atoms. For now, with this idea of formal charge being different than the octet rule in terms of how we view the bond, we're going to go forward and look at all the possible formal charges of carbon that you're going to run into in organic chemistry. So let's start by looking at the neutral form of carbon. Right? And we have many different ways. And earlier in the hybridization unit, the reason why I like to teach hybridization and formal charge together is that I can show you that these two things they interact, but they don't really interfere with each other. What I mean by that is let's look at the sp3 carbon. So here I'm not going to draw the carbon, just the intersection there. The sp2 carbon here, and the sp carbon, the triple bonded carbon. There. We'll look at those specifically. Now, as I've drawn them, there's no charge associated. So I've drawn them neutrally, and you can see that they all obey the octet rule, despite having different hybridizations. Now, from the perspective of formal charge, what we want to do is we want to compare the amount of electrons that atom has versus the amount that it wants. And we get that understanding from the periodic table. We see that carbon is in period 14, which tells us, as a hint, the last letter here, the 4, means that this carbon wants 4 valence electrons. Excellent. So if it has 4 valence electrons, it'll be neutral. That'll be where it's happy. If it has 5 valence electrons, that's 1 too many, it'll be negative. And if it has 3 valence electrons, it'll be short. Looking from a formal charge perspective, all of these different forms of carbon that we've covered all have 4 bonds. Of course, the hybridization is different, as we discussed, but it is 4 bonds, which means that these are equal sharing of electrons, and all cases of these neutral carbons therefore have 4 valence electrons. Awesome. Now let's look at the negative forms of carbon. Now, to have a negative form of carbon, we're going to want 5 valence electrons. And how are we going to do that? Well, let's compare all the different hybridizations, how that could look. With sp3 carbons, we need to trade one of those bonds for a lone pair. Remember that a bond is worth 1 valence electron and a lone pair is worth 2. So if I take that same molecule, I keep 3 of the hydrogens, but I lose 1 and I replace it with a lone pair. This atom now has 2 valence electrons here, so 3 bonds and 2 electrons from the lone pair. 1, 1, 1, and then the 2 that belong to the carbon itself. So now we have 5 valence electrons. So whenever a carbon has a lone pair, it is always going to be negative. And that's one hint. Carbon is usually pretty straightforward. It's always happy when it has no lone pairs. It's negative when it has 1 lone pair. That's also true for sp2 carbons. If we take a look here, I can draw the same molecule, but replace one of these hydrogens for a lone pair. This will give that atom a negative charge, and let's break down why. We have 1, 2, 3 bonds that give 1 electron each, as well as the 2 electrons of the lone pair on this atom. Once again, that's going to give us 5 valence electrons and a negative charge, as remember that carbon wants 4. And the same is true, of course, for the sp hybrid. Now there's no hydrogens there, and this is going to give a negative charge as well. So all that leaves us with is now the positive forms. Now, if carbon wants 4 valence electrons, in order to make it positive, we're going to have to remove one of those electrons. And that means that we're actually going to need 3. Now, this is where we are actually going to do something that we haven't done yet in chemistry. It's quite exciting. All right, we are going to do an octet violation. So it turns out that the octet rule isn't as strong of a rule as you might first think. It is always going to apply that if you break the octet, you're extremely unstable. Breaking the octet is a horrible thing to do from a stability perspective. But in order to make a positive carbon, you basically have to. Starting from our neutral carbon, you can see that we have 4 bonds. And because we have 4 bonds, there's no way that we can trade a lone pair for a bond. Recall that if we want to lose electrons, we need to trade lone pairs for bonds. But if there's no lone pairs to trade, we're simply going to have to remove one of those bonds. And that's exactly what's going to happen here. If we remove one of the hydrogens, we have a carbon that actually violates the octet. It only has 6 electrons around it from the 3 bonds. This gives the carbon a positive charge and produces what we call a carbocation. We won't be dealing with carbocations too much in the beginning of this course, but as we approach the reactions at the end of the course, you'll be seeing a lot of these. Note that the carbocation is actually not an sp3 hybrid anymore. Applying our rules from section 2.4, we can count that there are 1, 2, 3 groups around that carbon. The positive charge does not count. And so what that gives us is a hybridization of sp2. So as an overview for carbon, carbon wants 4 valence electrons, and it can achieve that by having 4 bonds. It can do that as either sp3, sp2, or sp hybrid. To make a carbon negative, you'll be adding a lone pair and removing a bond. This keeps the octet rule the same, while increasing the number of valence electrons to 5. And you can see that with all the different hybridizations. However, making carbon positive is an exception, and in order to do it, you need to break the octet rule and form a carbocation that is going to be sp2 hybridized. Now that we've broken down the rules for formal charges of carbon, let's take a look at the heteroatoms, including oxygen, nitrogen, and the halogens, to fully understand how formal charge works.